All right, so I came here as a postdoc in 2007, and what I want to do is begin by just telling you how I got into CNM. So I'll say, I know this is the NetMath seminar. My experience with anything like NetMath was CNM, so I'm going to talk about sort of my own experience. And I got into CNM in sort of a funny way. So let me give you my history. So I was an undergraduate at Davidson College, and I took linear algebra in 1999. And my instructor occasionally used some Mathematica in teaching linear algebra. That was one of the things that he was interested in doing, was having us do some actual computations as opposed to the kinds of computations you would do by hand. What I remember from that class, well, I liked linear algebra a lot. It was one of the reasons that I became a math major and now a mathematician. I didn't know that math was interesting because all I had seen before that was calculus 1 and 2, which I've only recently discovered is interesting. It wasn't the thing that lit my fire when I was an undergraduate. But one of the things I remember most about that class is at the end, we did this amazing application to image compression. And that stuck with me for many, many years. And long after I remembered how the actual application worked, I remembered that somehow or another, at the end of linear algebra, you can do this cool application where you take a picture from Mars and you can compress it using linear algebra in some way. So this is what I remembered about linear algebra. And so when I was a graduate student at Stanford, they had me teach Calc 1 for a long time. And then at some point, after I begged and pleaded enough, they let me teach linear algebra. And so we use sort of a traditional linear algebra text. It wasn't Lay, it was Otto Brescher's text on linear algebra. Has a lot of nice applications in it. It's a good text, I like it a lot. But what I wanted to do in my class was give my students a chance to see some technology used in that class. So it wasn't just going to be 3x3 matrices that they could row reduce by hand. I actually wanted to show them what it looks like when you take 100 data points and you try to do something with 100 data points. And so at the end of the class, I sort of came up with all these examples during that class. And then at the end of the class, I remembered that there was this image compression application. And so I wanted to remind myself how that worked and show it to my students. And so I spent some time. I contacted my former professor. I looked some things up. I realized the singular value decomposition was the thing that I needed to teach them in order to do this kind of image compression application. So we did that. We did the image compression. I was very happy about it. In fact, I was sufficiently happy about it that I decided I was going to use the code that I had developed for that class to do sort of a compressed version of myself that I would put on my web page. Because the next year I was going to go on the job market. And when you go on the job market, it doesn't hurt to have a decent web page. And it doesn't hurt to have a web page that has a little bit of splash to it. So I took the ideas from this class, and I did a compressed version of myself for my web page that has the cute property that when you roll over this image, you get sort of an SVD decompression of my picture.
You ready to try it?
Let's do it. This is essentially the web page that I had when I went on the job market. Occasionally I've updated it. So when I got here, I added a sentence that said, I am now a J.L. Dube professor of mathematics. And then when I left here, I wrote, I was a J.L. So every once in a while it gets updated just very incrementally. But for the most part, it hasn't changed because, I don't know, I guess I have a job now. So this is the image of myself that I put up. This is back when I was in graduate school. You can see how happy I was. Yeah?
I don't know.
A little more brightness.
Oh, it went away.
Yes, the dust filter is now resolved. OK, so this is what the picture of me looks like. And you can see up here, it may be hard to read. It says singular values 41, compression 30%. OK, and it has this cute property that if you put your mouse over this, it rolls through the various singular value decompositions for this picture. So it progresses through odd numbers or whatever. By the time you get to 25, you realize that it's me. When it's singular value 1, it does not look like me very much, or at least I think. So it takes a while to get there, but it's kind of cute, right? So, and I got jobs, so that was great. So I come to UIUC. I'm in the mailroom. I bump into Bob Muncaster. I've already been assigned classes for the fall. And Bob says, I was looking at your webpage, and I think you would really like to teach Math 415 CNM in the spring. And I said, OK, what is Math 415 CNM? He said, well, it's this active learning class. There's a lot of Mathematica. It's really very different from sort of a traditional classroom. And I said, thanks, but no thanks. I don't think I'm interested. Because I didn't know anything about being in an untraditional classroom. I was used to lecturing, and I like lecturing. It's sort of fun for me. I like to think that I'm funny and entertaining. So at least I enjoy it when I'm up there. But he convinced me that it was really something that I would like. And so later I asked him, why did you think I would like CNM? And he said, well, you have this picture on your webpage. This is like one of the things they do in 415 CNM. I traced back. It turns out that the reason that my professor as an undergraduate knew about this was that Todd Will knew about this because he was at Illinois, and he told the faculty members at Davidson College about this. So it's this really sort of interesting full circle thing that I didn't realize was happening. But I actually have deep roots in CNM, it turns out. And some of the things that I learned in linear algebra are influenced by the fact that Todd Will learned about this approach that Jerry Ull and others came up with for linear algebra. All right, so with all of that history said, we are now, we've done all of this stuff. OK, great. So I went to college. I went to graduate school. I've taught CNM 415 3 times while I was here. OK, so I'm relatively familiar with the courseware. What I want you to get out of this talk, I am not currently a CNM instructor. I don't work for NetMath. When I teach linear algebra, well, I haven't taught linear algebra since I left here. But the next time that I do, I will likely teach it in a relatively traditional lecture format. It's just what we have at our school. So that's what I'll likely wind up doing. But what I want to do is give some perspective on why participating in CNM or NetMath or some of these other environments has been really useful to me as an instructor, and some of the perspectives that I've taken away and the way that CNM has influenced how I think about not just teaching, but even linear algebra itself. So here are some of the bullet points. So here are some of the things that came away from my time at CNM. One was the idea that technology, when I was an undergraduate and you talked about technology in a math classroom, it was about TI-89 calculators. Maybe if you had Mathematica at your school, then if you logged into the appropriate computer and you used one of the 5 licensed copies of Mathematica, you could do all the great things that Mathematica could do, right? Today, that is not so much the case. One of the things that's great about technology these days, it's becoming at least seamless. Things are happening in the cloud. You can do things on a browser. So that's one of the things that I think really will transform the way that math gets taught. The fact that in order to have access to these computational tools, the fact that you don't have to have specialized software, that all you really have to have is a browser, makes a big difference. And there are a lot of programs out there that are already in the browser that you can use to do some interesting computational things in your class. CNM had students write more than I think any other math class that I taught while I was here. There was a lot of writing in a CNM class. And it's not always formal proof type writing, but it is sort of the spirit of what proof is. So it's not sort of the proof that a mathematician would call a proof, but it's a proof in the sense that you're asking students to come up with reasonable explanations in the language of the course that their peers would understand, which is really, when you think about what a proof is supposed to be for a mathematician, we just have a different peer group. The language that we speak is different from the language that an undergraduate math student speaks. So this is really taking that idea of proof, but putting it in a context which is maybe not quite so mathematical, something that's like, I don't know, proof for the masses or something like that. Let's see, so you've already read all of these things already because I talk slower than you read. But just a couple of other things that I want to point out here is that if you want to experiment pedagogically, you do not have to come up with some brand new idea that just you thought of. So using new ideas in the classroom is not about you coming up with new ideas necessarily. A lot of really clever people have thought of a lot of really good ideas. And almost all those people are really happy if you just steal their ideas. Okay? So, and I think almost nothing that I'm going to talk about today is original to me. It's stuff that I heard about from other people that I just tried. Some of it's been very successful. Some of it's been less successful. But the good news for me was that if I wanted to use some new technique in the classroom, I didn't have to come up with it. Someone else had already done the hard work. So all those things are available basically everywhere. And then the other thing is Math CNM really made me think hard about what a service math class is supposed to be about. And I think this is one of the things that the mathematical community as a whole is really going to have to address in the next 10 to 15 to 20 years.
Hear, hear.
What is it that a math student is supposed to come away with? Why is it that everyone takes Calculus 2 or whatever it is? What skill sets do we want students to come away with when they've taken a math class? The fact that 415 CNM does linear algebra in a different way really forced me to think about some of these issues in a way that I really appreciate now. All right, so I'm going to give you my perspective on what Calculus and Mathematica C&M was about for me. I haven't sort of passed this across anyone to verify that it's exactly what C&M is supposed to be about. So my apologies if it's not what it was supposed to be, but this is just how I feel about it. So I guess I have the microphone, so you can't stop me. So one of the important things is that it really is a student-led environment. Students are the people that are in front of the wheel. They're the ones that drive down the road. If they're going to careen off to the side, it's because they're at the wheel careening off the side. If they're going to do great, it's because they're willing to put in the effort. So it's far more student-driven than any other class that I taught before then. It's not exactly, it's not structured like a traditional lecture class, of course. It's also not 100% sort of loosey-goosey, free-form, do what you want. There is structure that's built into it, especially when you teach a version that is, that happens during a semester. There is a progression that you have control over. I made sure that my students had checkpoints essentially every week, just to make sure that they didn't realize they had a test the next day, and so they're going to learn 4 chapters of material in 5 hours, right? But so there's far less structure than a normal class, but it is not entirely up to the students, I suppose. Students also work in teams far more than in a regular class. When I teach a traditional lecture style class, I occasionally have my students split up and work in teams on problems. This class is all about sort of working in teams almost on all problems. It's really about doing things as a group. Like I said before, there is lots and lots of writing. There is lots and lots of explanation. Students are expected to be able to talk about what they're doing in a sensible way. You've all taught math classes before. You know it is really hard for students to speak mathematics correctly, right? We have a very specialized vocabulary. We say certain words and they mean exactly particular things. I'm working with a thesis student now who's writing her thesis up. And it's funny, when I read her work, occasionally she'll say a word which is not the right word from a mathematician's perspective. If you give this to a non-mathematician, they understand what that word means. But my mathematical ear hears the word for instead of the word, whatever, since or something like this. And I interpret, I go into math mode and I say, I know exactly what that word is supposed to mean, and you don't mean that word, you mean this word. And she says, okay, I guess. I was saying it the way that I think about it. And no, that's not how we talk in math, right? It's hard to get students to write mathematically correctly. But C&M is a lot about forcing students to do that. It's not easy, but I don't know, nothing that's worth doing is easy, right? It's not exactly an axiomatic approach to mathematics. That's the way that mathematicians think about math. What are the ground rules? We'll start with very basic ground rules and we'll build up from there. So it's not exactly that approach. At the same time, it is not totally hand-wavy. There are some black boxes in 415 C&M, but at some point the black boxes get filled in. Okay, so there's some buy-in at the beginning, but hopefully by the end of the semester, for students that are motivated, those gaps get filled. The last thing that was great about C&M for me is that it really embraces the idea that computers are good at computing, which is correct. and since so much of technology is now universal and in a browser, it is increasingly sensible to allow computers to do computing. So this is not to say that it's not worthwhile for a student to know that 8 divided by 2 is 4. I have had classes before where I say 8 over 2, what is it? And someone breaks out a calculator, and I have to tell them it's okay occasionally to just think and figure out what it is. So I'm not saying that they shouldn't know how to do some computations, but at the end of the day, when you think about how mathematics really gets used in the real world, if a problem is interesting enough for a human being to consider, it's probably too hard to do by hand. It's probably sensible to have a computer do the calculation and then have the human do the interpretation. That's what we're good at, right? The interpretation. C&M really embraces this idea.
So would you suggest, therefore, that instead of saying 8 divided by 2, you give a 25-digit number divided by a 39-digit number?
Do I think that that's...
Well, because only a computer...
Oh, yeah. I'm just saying that, in the context of a traditional class, yeah, I agree. Yeah, you could do that.
But you realize that a 39-digit number can't be handled by a 4-function calculator.
Right, yes.
So now it gets interesting.
Yeah, I know. I mean, one of the classes that blew my brain out of my head when I was an undergraduate was numerical analysis, because I grew up trusting that computers knew what they were doing. And in numerical analysis, you start dealing with issues like when is a calculator lying to you.
Would you suggest that in a computer-assisted course you always do some necessary numerical analysis?
I think when you start doing calculational things, and I'm going to talk about this in a second, anytime that you have real-world problems, at some point you do need to start thinking about issues of, can you trust the computer or not? So I'll mention exactly an idea like that that comes out of 415 CNM. But yeah, I think at some point, if we're going to use computers to compute things, we should also understand that computers are machines, and they are programmed with algorithms that you need to understand at some level in order to have the ability to make an interpretation, right? OK. What is 415 CNM? So 415 is linear algebra. What is the perspective of the Calculus and Mathematica version of 415? Essentially, the perspective of that class is this theorem, the singular value decomposition. This is a theorem that occasionally gets taught in linear algebra classes. I have asked a lot of my colleagues that teach sort of traditional lecture versions of linear algebra, and I asked them, do you do SVD? And the absolute best response I think I've ever gotten is, I mention it in the last week of class. For the most part, people don't really talk about it a ton. So if you've not seen it before, the idea is that every matrix whose coefficients are in the real numbers can be factored as a product of nice matrices. So this matrix on the left is what would be called an orthogonal matrix. It's an n by n matrix whose columns are an orthonormal basis for M space. This matrix V on the right-hand side is an orthogonal matrix inside of n space, so it has an orthogonal basis for Rn. And then here in the middle, there are some non-zero numbers and then zeros. Okay, so so the idea of 415 CNM is to begin with this. You start here, and you try to interpret linear algebra through the lens of the singular value decomposition. Okay. Now, of course, that is not to say that on the first day of class you write this down, right? Because this would not make a whole lot of sense. So what you do instead is you sort of motivate what objects like U and objects like V transpose and objects like this are. So you start with sort of a geometric perspective on linear algebra, and you build from there. Okay? So it is not revolutionary to try to understand linear algebra from a geometric perspective. Right? This is not something which is wildly different from how most people think about linear algebra or teach linear algebra. But most people don't begin with this particular geometric understanding of things. So 415 CNM begins by thinking about what does it mean to multiply a vector by an orthogonal matrix? What does an orthogonal matrix do to the ambient space? Right? How can I interpret what it's doing geometrically? What does a matrix like this do geometrically to a space in terms of stretching and shrinking and those kinds of things? Okay, so it gives sort of a geometric interpretation of what these matrices are, and then later it sort of fills out why you should expect matrices to do that in the first place. Okay? And I'll point out the geometric actions that these matrices perform are all of the actions that students already feel good about. Right? So to say that you're living inside of 3 space and you take 3 space and you shift it around like this, students essentially know what you mean. I mean, they may not get it when you do this, but if you show them a perp frame for R3 and then you move it around like this, then they'll say, oh, I know what you're doing. You're just sort of rotating things around. So there's a good sense for what happens in all of these settings. All right, so it begins with a good geometric understanding. I'll point out that the SVD, if that is your perspective on a linear algebra class, I think actually in the courseware for 415, the singular value decomposition is called the holy grail of linear algebra. So the idea is somehow or another you should be able to interpret all of linear algebra through the lens of the singular value decomposition.
It's called the fundamental theorem of algebra.
Of linear algebra? Yeah. Yeah, I think this is I was flirting with putting that up on a slide, in fact. Yeah, that's essentially what it's supposed to be, is like a fundamental theorem. And we'll think about ways that it is, but just I'll point out, if I give you a singular value decomposition for a matrix, then you can get all kinds of traditional things that you would care about a matrix. So all the stuff you would learn about in a regular class, like rank and inverse and transpose. It gives a really nice geometric interpretation for change of basis. It's not exactly change of basis, but this idea of understanding a matrix by factoring it in terms of different things, where you might want to change your perspective on the space so that the action that gets performed is simpler than if you look at sort of the traditional basis on the space, right? So it gives really good geometric interpretations for all of those things. It also gives you a good interpretation for how you can build matrices that perform a certain action. So I don't know if you like to ask these kinds of questions in a linear algebra class, but one of the things that I like to do to see how well people understand change of basis or those kinds of ideas is to say, I want a matrix that does the following thing inside of R3. Please build it for me. So I want it to sort of project onto a plane, but the plane isn't nice. It's some weirdo skew plane, right? So I like asking questions like that. And SVD gives you a great way for coming up with good intuition for how to answer those kinds of questions. Right. The SVD gives you a way for finding orthonormal bases for the kernel of a matrix, the kernel of the transpose of the matrix, the column space of the matrix, the orthogonal complement of the column space of the matrix. All that stuff is just right there in the singular value decomposition. All those things that you would care about just get read off. You don't, and it's not that you don't have to do thinking. It's that you learn to think about things in a certain way where if you really understand what this matrix factorization means in terms of actions, it makes a lot of sense that if you just look at columns, let's say, that correspond to certain singular values, then you can just read off what they do, right? In fact, this is one of the things that I was surprised to find when I first taught linear algebra that I didn't understand as an undergraduate, is that when you learn theorems that are about factorizations of matrices, they're really there to help you interpret a geometric action in terms of smaller, simpler geometric actions, right? And that's exactly what's happening here. By really understanding what this factorization means, you have a good reason for believing that you know orthonormal bases for the kernel of the matrix or something like this, right? It just makes sense because the perspective is correct. OK, one of the things that I think is absolutely most important about this perspective in the singular value decomposition is that it asks students to deal with the fact that data in the real world is fuzzy, OK? We are not good at observing things, either because our machinery is not good at observing things or because we as human beings are inherently flawed, or if you really want to get down on the nanoscale, because physics says you can't observe things very well, right? However you want to slice it. When you're a scientist, when you're a real human being dealing with real data that you're trying to interpret, you're going to have mistakes in your data. That's just the way that it goes. As mathematicians, we don't like to think about that. If someone gives you a matrix, they've given you the matrix, you should believe in all of the numbers that are in that matrix, and you should interpret based on that. This is not what life in the real world is like. So the singular value decomposition gives you a way for interpreting this kind of fuzzy data. I'll talk about this in a second. And then the other thing that's so great about the SVD is that it gives you nice techniques for approximating matrices. Okay? So the punchline of a Calculus 2 class, at least when I teach it, is that Taylor polynomials are good approximations for functions, at least I suppose, assuming that your function is nice enough, right? The singular value decomposition gives you that same kind of theorem. You have some matrix. It gives you a way for coming up with, it's not exactly a Taylor approximation, but it might as well be, okay? It gives you a way to sort of truncate the matrix in a meaningful way so that you have an approximation that is somehow better than the matrix that you began with, right? Oh, and finally, I don't know if you, when I taught linear algebra the first time, and they would give me some like the book would have some applications of linear algebra. I remember some of the first applications were applications from chemistry. And I'm not saying that this is not an important question, but the application was something about like you have some chemical equation that's trying to get balanced, and you have a certain number of molecules of water, and you need to know how many molecules of something else you get so that the reduction actually does what it's supposed to do. All that stuff is great, but it's not interesting. It's not, I don't know. It's maybe. I mean, if you're a chemist, sure, but it's just, it's not real world. It's not real world in the sense of like I'm going to go get data and do something with it. It is in some sense for me. It's too simple of an application to be called an exciting application, right? Mathematics is great because you can take problems that are ill-conditioned, that don't have good answers, and you could answer questions that don't have answers, right? And some of the things that you can answer that do have answers, these sort of applications that are very clean cut, all that stuff is great, but I think what's really exciting in math is answering problems that shouldn't have a solution. Yep?
I have a question. I Did you check how many chemists there were in the room?
In that room, this was a class of first-year students, and I don't think that there were very many chemists at all.
So then you're right, it's irrelevant.
Yeah. Well,
But
and
so
again,
the
it's not that it's not an important, it's not that it's not a good illustration of what linear algebra does. It is just so fit to linear algebra that I think it sort of misses the point of one of the things that linear algebra is so great at, which is not just solving linear equations that are solvable. It's trying to figure out what you do with a linear equation when there is not a solution, right? This question of least squares, to me, is really the thing that makes linear algebra so exciting, is because normally in a math class, if I ask you to solve a quadratic polynomial and you don't believe in the complex numbers, I say solve this thing, and you say, well, I can't because b squared minus 4ac is negative. OK, that's fine. What's exciting, though, is the idea that you could sort of inflate the real numbers to a larger system where you do have solutions that make sense. In the same way, least squares is a way to solve linear equations that shouldn't have solutions, right? But again, in the real world, problems don't have solutions because the problems you're dealing with come from data sets that aren't correct, right? So you never get real solutions. So knowing how to deal with that, I think, is one of the things that's really important. Let me give you some examples of some of these applications that I'm talking about here. All right, so this least squares problem. So you have a linear system AX equals V. You have the matrix A, obviously, and you have the matrix V. And you want to find a least squares solution to this. If you have a singular value decomposition, there is something which is called the pseudo-inverse of the matrix, which gives you the minimal norm least squares solution for that system. Okay? And you write it down in a very natural way. If you think about how you would undo the geometric action of an SVD decomposition, it is not hard to see that this is exactly what you ought to do. Essentially, you punt on the fact that some spaces get crushed. But on the things that don't get crushed, you just reinflate them. Okay? So this is called the pseudo-inverse. And again, if you know an SVD, then it doesn't take a lot of thinking to write down a pseudo-inverse. And pseudo-inverse is important because it answers least square problems, which I think are one of the really big applications here. Also, you deal with more interesting questions even than how do you solve a problem that has no solution, which I think is already interesting. But it forces you to ask the question, is this really the solution that I should be considering? Okay? So the theory says if you want to solve a least square solution to an equation like that, the theory says you should look at this vector. Okay? But given that we live in a world of fuzzy data, what you really should be asking yourself is, how much do I believe that the matrix that I'm dealing with is really the matrix that I tried to observe, right? How can I account for the fact that my data might be off a little bit? And how does that affect the linear system that I'm looking at? In other words, the theory says this is the right minimal least square solution. But should I really be trying to solve this system so precisely? So what do I mean by that? It turns out that if you make very small changes to the entries of a matrix, it can have an enormous impact on whether or not that matrix is singular. Okay? So traditionally, if you teach a linear algebra class and you ask a student, how do you know if this matrix is singular? Then the student will say, you compute a determinant, and the determinant tells you whether or not the matrix is singular. And that's correct, right? So you would think that if you wanted to know whether or not your matrix was close to being singular, you would compute the determinant. And if the determinant was 1,000,000, that determinant is so far from being 0, right, that it is definitely not singular. It turns out that you can have a matrix whose determinant is 1,000,000, and you can make one tiny change to one part of the matrix, and all of a sudden, that matrix becomes singular. So a tiny, tiny change to one entry of a matrix. Yeah, I know, but to a student, right? If you said to a student, oh, how am I going to check whether this is singular? Take a determinant, the determinant's big, of course it's not singular. Students will say, yeah, of course, right? Intuitively, if you kind of believe what a determinant is supposed to measure, then you think that's reasonable. But when you do it with this SVD way, you have a better way of understanding whether or not something is close to being singular. So there's something called a condition number for a matrix. Let me just give you a quick example. You can ask the question whether or not this matrix is invertible. And if you know linear algebra well enough, then all you have to do is look at these columns and see if one is a scalar multiple of the other. And it's not. So everything should be good to go, right? But things are not so good to go in this matrix. So let me, in the spirit of the browser does all things, I just want to point out that Wolfram alpha, if you ask it nicely enough, will do singular value decompositions for matrices. Okay? So 15 years ago, 10 years ago, 5 years ago, trying to do an SVD meant that you bought a copy of Mathematica, or you were good enough with Linux that you could install some computer algebra system on your own. But now that Wolfram alpha is around, you just type in, give me singular value decomposition, and Wolfram alpha says, yes, thank you. Right? And in fact, not only that, it even formats it nicely for you. Right? I mean, Wolfram alpha spoils us because it even writes things in a way that sort of falls right in line with how we think about singular value decompositions, which is great. For this particular matrix, you can see one of my singular values is humongous. One of them is relatively small. This is an indication that a small change in the values of this matrix can have a big impact on whether or not it's singular. So this condition number is sort of determining whether or not I should really believe that the data that is represented in this matrix actually represents a system which is singular or not. Okay? All right. Uh-oh. I hope you liked my talk so far.
Because here's a quick review.
Yeah, that's right. Where have we been? OK, great. So the thing that I want to point out is that if you observe a matrix in nature, rarely will you observe a singular matrix. Because as soon as you start making small errors, you almost certainly get rid of those zeros that contribute to your matrix being singular, the zero singular values. So at some point, you have to deal with this fact. Right? If you're really going to use linear algebra to do stuff in the real world, you have to be able to know whether or not you should trust the data. So this sort of gets to your question before. Do we need to teach students about the numerical processes that dictate the sort of algorithms that we teach them? I think it's important, right? I mean, if you really want to understand how to use this stuff, yes, you need to have some understanding of what those things are.
I was trying to say that it should be taught in the math department, not across the street.
I think there's a natural place for mathematicians to do this. Yeah, you do not have to be the person that programs something like this to understand why numerics are important, right? OK. Let me, shoot, I know it's going to take me forever to navigate, and soon I'm going to have to make my pause. I'll punt on giving you another example of a real-world interesting application. It's not fast enough, I think, to make a difference. Yeah, we're not terribly, I still got more to go. So at the end of this, maybe I'll show you some other interesting applications of SVD, just so you can see what I mean when I say a sexier application than just looking at some chemical equation that you're trying to balance. Okay? All right, so those are the things that I think are great about 415 CNM, and particularly this perspective of the SVD as the black box that you use at the beginning of the course that helps you interpret all the phenomena that you would normally see in a linear algebra class. This is not to say that this SVD approach is something that everyone is excited about. Obviously, people are still teaching linear algebra the traditional way. So there's not everyone thinks that this is the right way to do things. One of the complaints, I think, is that students become tethered to the computer. All right, so you can teach a student how to row reduce a 2x2 matrix or a 3x3 matrix if you want to. Or you can just tell a student that you could have a computer do it. And I see good reasons to do sort of both of those things. But when I've taught 415 CNM before, I decided I was just not going to spend a lot of time teaching my students how to row reduce matrices when they could have a computer do it instead. I mean, rarely is it the case that you come across a 2x2 or 3x3 matrix that you want to reduce, and you don't have a computer at hand, right?
Let me just throw something in here.
Yeah.
This is dear to my heart. It depends on the student. For example, if you're developing teachers, you probably should get them to do row reduction by hand and writing a Python script to do it, because teachers need to understand the algorithm.
Sure.
If you're doing engineers, then you might as well use a computer, because any problem that they're going to handle is going to require a computer.
Right.
And luckily, engineers always can hire a mathematician to check the mathematics.
Yeah. Well, I think this gets back to the idea of what does it mean to teach a service class? And how do you keep your audience of students in mind when you're determining how you teach something? Is this the approach that I would take for a student who is going to go on to graduate school in mathematics? No, I would like them to take the most abstract linear algebra class possible, right? I don't want them to row reduce a matrix because I don't want them to see numbers, basically, right? But if you're teaching a class for engineers or chemists or whomever, if you want to show them stuff that's closer to what they're really going to be dealing with.
These same PhDs are going to have to eat and drink. So they need a job.
Yep.
And then they're going to be teaching engineers.
Sure.
If they're lucky.
Yeah, but if you've gone through, if you're a mathematician, if you think like a mathematician, you can come back and digest this stuff and be OK with it, right? So it's not that this perspective is not important. I think this is a perspective that, even people who sort of subscribe to the traditional understanding of linear algebra, this is a good thing to understand. Because as mathematicians, you don't want to understand things in one way. You want to understand things in 50 ways. That's what makes mathematics exciting, right? OK, so one possible complaint is that students can get tethered to computers. You can choose to tether students. You can choose to teach them to do it by hand. But it's reasonable to say that if a student doesn't know how to row reduce, then maybe that's, I don't know, maybe that's not ideal. One of the other things is that the 415 courseware uses language which is different from most other linear algebra texts. So words like hanger and aligner and stretchers and those sorts of things are not the kinds of words that typically get floated in a linear algebra class. So for some people, this is a very big issue. And I'm not, yeah.
One is that if you actually do a web search on hanger and aligner, it's making its way into the literature.
Oh, yeah.
OK.
It is formal research paper.
No,
It's
that's
making its way
fine.
into the
I mean,
literature.
that's how mathematics works.
And I'm sure that when you taught 415, you did this as well. I taught the standard terminology right alongside this quote-unquote non-standard terminology. The standard terminology represents matrices as static entities. It describes the matrix. Our terminology describes the action. They're completely compatible.
Sure. Now, so all of these.
Actually, the Mathematica notebook should give both names at all times.
Well, you can find both names.
No,
They're not
check
always
it.
used simultaneously.
So I think this is a topic that's worth discussing, and I think I can understand people that would have this gripe. I'm not trying to side on one side or the other. I think if someone really understands something and they use some bizarre name for it, I would rather have a student that uses a weird word for kernel. But when I say, I don't understand what you mean when you say the Abu Dhabi of a matrix, and they say, oh, the Abu Dhabi is when you do blah, 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 and you get 0. And I'll say, oh, we call that a kernel. And they'll say, oh, we call it an up. And then fine, we know we can translate, right? If you teach them a word and they understand what the word means, then they can have a conversation, right? If you teach them terminology but they don't get the terminology, then it doesn't matter if they use the same word, because if you say kernel, all they're going to hear is, I know that I heard that word at some point. But they're not going to know what it means, right? So.
Army officer.
Army officer?
Colonel.
Colonel, yeah.
Or chicken.
Chicken is what I think of. All right. SVD doesn't exactly fit the traditional model for what an axiom is. A black box at the beginning of a course should be something that is intuitive and believable. 0 is not equal to 1 is a great axiom in number theory.
Let me dispute that, just for the sake.
Sure.
That SVD decomposition coming out of alpha is as good an axiom as any. It's perfectly obvious. It always works. If you put in the same numbers, you always get the same answer. Must be true.
OK. I mean,
it's no better than the fifth, no worse than the fifth postulate of Euclid.
I mean, we can debate what it means to have a reasonable axiom or not. But
I'll let George tag me in. Do you actually start teaching linear algebra course by giving the axioms for a vector space?
No. So one of the things I was going to say was, when I teach my students to row reduce, I spend a little time saying, like, here is why it's reasonable to do these operations without changing the system. But I never, ever prove that a system of equations has a unique row reduced form, right? There's a lot of black box that goes into linear algebra. So deciding what you believe is a reasonable black box at the beginning is sort of a matter of preference. So again, when I say that these are complaints that people can make, I can understand both sides of the perspective. I'm not trying to say one way is right and one way is wrong. But these are some of the reasons that people might not be as crazy about this. Not everything is so clearly tied to SVD. I think you can make similar statements about, is everything clearly connected to row reduction? Yeah, you can use row reduction to do everything. Is it always the right perspective? Maybe not. Right?
How do you calculate pseudo-inverse with row reduction?
For instance, yeah, great. So, I mean, these are all the way that you answer these questions. What is pseudo-inverse? Yeah. So what you would normally teach in a class is you do the normal form of an equation, you solve that thing using row reduction, and then you look inside the space of solutions, and you find some linear thing, some least norm solution. Yeah, you can do it, but yeah, the perspective is different. Okay. All right. So the epsilon delta debate. If you ask an instructor of calculus, is it worth teaching calculus students about epsilon delta proofs? Mathematicians like to say yes, everyone should see epsilon delta at some point in their life. students will say, please don't ever show me an epsilon delta in my life. How am I ever going to use this?
Students don't do that. It's their advisors across the street that do that.
OK. Some students will say, I do not want to see an epsilon delta.
Epsilon and delta.
Yeah, right. So
But they've been conditioned to hate them.
I think the same perspective comes up when you teach linear algebra. How much is it important to teach them linear algebra from the mathematician's perspective, as opposed to teaching them linear algebra from a sort of user's standpoint, right? And when you teach a service class, at some point you have to answer that question. Am I teaching the service class to teach these people to be mathematicians, or am I teaching the service class to teach people how to use mathematics?
Well, we implicitly answered that. That's why we have two different classes. 415 is applied.
Yes, but every student should take both.
Good luck shoehorning that into the.
All right, so I'll say that.
Scott is here. He can manage that, right, Scott? Every undergraduate now takes both.
So I'll just say that there is an audience for which understanding things not from the rigorous mathematical perspective makes sense.
Actually,
right?
I would call this the theological debate, not the epsilon.
All right. All right, so just in closing, I'll go through these last few slides pretty quickly. This is supposed to be about me talking about how C&M has inspired me in classes that are not C&M classes. So what's the takeaway for me outside of a C&M classroom? How do I take some of these ideas and bring them into what would be considered the traditional class? So I'll just run through a few examples. Again, none of these ideas are really unique to me. So I taught 453 here, elementary number theory. And I had a few goals when I taught it. Two of these goals were sort of coming from the fact that number theory is this great discipline where students are able to make observations. Everything is concrete enough that it's really possible, and in some sense foreign enough to them, that it's possible for them to come up with conjectures on their own just by looking at data without sort of being influenced by maybe having a lot of sort of background noise about number theory. There's a lot of background noise about, let's say, calculus, right? They've sort of learned calculus in high school, then they learn it again in college. There's a lot of sort of baggage that goes along with that. Number theory, most people haven't thought about very much. But everything is concrete enough that they can come up with their own statements and questions and those sorts of things. So I wanted to encourage students to do that kind of question asking. And I wanted also my students to be better talkers of mathematics and presenters of mathematics. So what did I do? I had a class wiki. There's something called wikidot.com, which would actually render LaTeX. I guess Moodle does this as well. I was using wikidot.com. So I wanted my students to be able to format mathematics nicely. It is hard to read mathematics if the symbols aren't correct. It sounds silly, but you got to write it right in order for it to make sense. The other tool I had was I did student presentations. So the last 2 to 3 weeks of the class was devoted to students working in teams where they would have 50 minutes during a 50-minute class period where they would have researched some topic that they picked on their own, and they would explain it to their classmates.
In that same hour?
No. So they would research it 3 weeks ahead of time. They would give me a practice talk. I would say, oh, you need to think about this when you're talking to an audience. So what came away? What happened because of this? One was that students, I was really amazed. They loved the presentations. I still get emails from students saying that was the thing that they liked the most while they were at UIUC, was the chance to do these presentations. So they just loved that. Some students took this inquiry part pretty seriously. They tried to come up with conjectures on their own. Other people's didn't. Even the ones that didn't take it too seriously did probably more independent mathematical noodling around on the internet than they would have otherwise. Some students were better at talking math than others. This is not a big surprise. I got to number theory. I got to Wellesley, and I wanted to teach number theory again. This time I wanted to use what's called an IBL method for teaching, inquiry-based learning. This is sort of like a proof immersion experience, sort of like you would have a language immersion. This is like math immersion, essentially, IBL. I also wanted my students to not just be writing proofs, but also to be reviewing proofs that other students wrote, peer review, which is what we do in mathematics. So how did I do this? One was I used this technique, inquiry-based learning. The other was I did inter and intra-campus peer review. So I had my own students critiquing the work of other people in the class. Simultaneously, a state away, I had a friend that was teaching number theory with the same textbook, and we would exchange across college. So my students would critique the work of his students and vice versa. So we did that a couple of times during the semester. What was the result? Middle tier students were served extremely well by this format. People that may not have traditionally succeeded in math class actually did great in this immersion experience. Top tier students probably could have been served better with a traditional math class. In some sense, the students that were already thinking like mathematicians, they're able to digest things fast enough that I could lecture and they get it. It's the students that have a hard time getting it when I lecture. Those are the ones that really got served the best. Student proof critiques weren't actually, they did not improve that much over the semester. Students were really good at critiquing punctuation and grammar. They loved that. They were not as good about critiquing sort of the mathematics behind what other people were writing. They would gravitate to the easy things that were the easy sort of critiques. And they would shy away from saying, your idea is wrong, right? Because they may have thought of it in a different way, and they weren't always willing to sort of go through the process of trying to think like the other person. I wish that I could have figured out how to make that better. But some students liked the IBL environment. Some students really did not like the IBL environment. And finally, this inter and inter-campus peer review was an absolute pain in the butt to administer. Trying to come up with anonymous peer review for 25 of my students and 30 of my colleagues' students, making all of this stuff blind, managing the PDF submissions, grading other people's critiques, it was a disaster. It took a really, really long time. Certainly for the payoff that I got, I think it was not worth it in the end. But an interesting idea. I taught Calc 2 last semester. Our department was running low on grading funds, so I wanted to not have a grader. I also wanted my students to get better homework feedback, because as it stood, an undergraduate grader would look through their homework. They would look to see if the answer was right at the circled number was correct. If it was, they got a check mark. If it wasn't, even if it was correct but not expressed in the right way, it would often get marked off. This is very unsatisfactory. And of course, this also took a week for the feedback to come back. This was not great. So I used WebWork, which is an online homework system that the AMS or MAA manages. The results were great. First off, students love hating WebWork. So it's kind of nice to have a straw man that you can say, oh, that WebWork. Surprisingly, by the end of the class, all my students almost uniformly said that they really found WebWork extremely important for their understanding. So even at the beginning, they would complain and moan that WebWork would constantly tell them, no, you're wrong. By the end of the semester, they really appreciated it. For the first time ever, my students wrote down the correct indefinite integral for 1 over x dx. WebWork does not say that it's ln of x. It will not accept that answer. And the fact that WebWork would not accept that meant that students finally took the absolute values seriously, which is, I don't know, cute. But it's kind of nice that a computer saying no meant that they really had to address an issue, that they would often say like, oh yeah, some absolute value thing, it's not important. One of the things I was amazed about, student writing, they didn't hand in their homework to me, but if they wanted to come talk to me about their homework, they had to write things up. The difference in the quality of their writing and how organized things were went up dramatically by the end of the semester. And the reason was, if they didn't get something right, they had to go back and read their own work in order to figure out what they did wrong. And the fact that they had to review their own work meant that they were invested in writing things more neatly, which is kind of an interesting and unexpected consequence. All right, so it's that time already. I have one other thing, but it's essentially, I'll show it to you. The results, question mark. I'm doing something in my class right now, basically. I'm not sure what the outcome is going to be. Well, it's a proof class where I don't have to teach them epsilon delta proofs, right? I'm gonna sort of give them a broad view of mathematics. What are some of the basic things we talk about? Functions, equivalence relations, basic things about inequalities. What is proof by induction? What is proof by contradiction? But not in the sense of, by the time you leave this class, you must know that the limit of a product of sequences is the product of the limits or something like that. So it's not something that there's content that needs to carry over to the next class. That's what I mean by content free. I get to sort of create my own sandbox. Yeah, it's exactly what it is, right? It's not that they're not learning things. It's that the things that they're learning are all skeletons that they can attach things to later.
If they remember it.
Hopefully, yeah, right. Yep.
I think that if can you go back to the previous
Sure.
slide, what this whole thing with the standards for writing arrays reminded me of is this concept of ownership of knowledge, that at some
Where
point people
does it
still
say that?
develop ownership for what they produce, and a lot of times in classrooms, you get your 80% and you go on and it doesn't really matter, whereas if you actually ask them to read over what they write, then they become owners of what they produce, and that people, I think, tend to become much more uncomfortable with saying just crap if they know that this will be read by
Let me
people
mention
and
something.
they'll have
No, I think that's exactly right. Yeah.
Andrew,
Yeah.
last night I started telling you about 347, 348 here.
Mhm.
I didn't know anything about it. So Math 347 is kind of like this. It's interesting that it's 300 at Illinois and 100 at Wellesley. That's good. However, that course is by D'Angelo West, and of course it's got epsilons and deltas up the wazoo. And what happens is that the highly ranked instructors never get out of algebra. You see, it begins with basically algebra, number theory, prime number theorem, and so on. And then it's supposed to seg into enough analysis so that the student ends up not just being blown away on the first analysis question.
Right.
And so what, as I said, so the result is that if you want to do it carefully, you can spend the entire semester on one proof
Yep.
until they get it.
Right.
Or, and so the 48 part gets even harder because now you put in a writing component. And now they not only have to write in an understandable way, but it has to be correct, syntactically and mathematically correct.
Yeah.
It's still not original proof. That comes, I guess Resnick isn't here. That comes in another course yet, but only for the math majors, where they actually solve problems that haven't been solved.
Yes, right. No, when I taught this class, there are 13 chapters in the book, and I have however many weeks I have. I spent, I think, 4 weeks on the first chapter. Because at the beginning, you got to spend time saying, like, 100 times a student begins a proof by assuming what they want to prove and manipulating it, right?
It works very well.
Yeah, it does. It's great. And you have to beat it into them, and it just takes a long time to do that. By the time you get to the end of the semester, if you want to, put the gas on a little bit, you can. But one of the things that's nice about not having to get to something is that if I just don't get to stuff, that's fine. If I have to spend more time making them really understand that you're not supposed to assume what you want to prove, then that's going to actually serve them later better.
Now, can this be translated into machine learning?
This kind of thing?
Yeah.
Well, this is the problem with this peer review stuff that I tried to do in my number theory class. At some point, you have to deal with administration. If you ask students to write stuff, at some point, you have to have somebody reading stuff. And that somebody should almost certainly be you or a qualified mathematician. It's not to say that their friends can't give them reasonable critiques, but at some point, someone who has authority needs to say.
See that little apple, there's still one in the
Yeah.
works. That solved a similar problem with our elementary school teachers and early childhood people. They take one math course. And it solved the following problem. These are the students that really have math phobia maximum.
Yeah.
And that is, not only do you want logical thinking in mathematics, but you also want the self-analysis, the meta-logical thinking that determines whether what you have thought is truly logical. And we decided, we being Graham Evans and the people down here, that's how this lab started, we decided that we'll just remove one of these components by teaching the students how to program. Because now, if it's not logical that they put in, the thing will say something silly like syntax error, a dumb computer doesn't know what I'm trying to say. But it's not a critique, it's not a criticism of their abilities, it just says you didn't do it right.
Right.
So if one could figure out with some of this AI stuff that people are developing, see, Plato was close to doing that way back when, and then it got killed off and it died, never really got properly revived. But if you really could try to automate some of this, right, then it would be a viable thing for NetMath.
There are some things, you've got your automated theorem provers where you can put in your proof and it can try and verify it for you. Grayson's working on stuff like that.
There are also proof assistants.
Yeah, but those tools are actually, so it kind of reminds me on one of your previous slides when you talked about Math 453, you said, people have kind of a somewhat close enough of a connection to it, students do, but they haven't seen a lot of it, so they can start experimenting. It seems to me now that we're getting close to a point where we can do the same thing for algebra, for example, with group theory. When I was taking an algebra course, I didn't have tools where I could just get some group and pick 2 elements and multiply and see what I get in an experiment. But I think that the time is coming for that.
Yeah.
So it would be really nice to see if there was a similar slide in a couple of years with Math 417 on it, and here's students were experimenting with these sort of things. And
Yeah.
But look, has anybody ever attempted to dissect a proof into lines, permute the lines, and have the students reorder them in the correct order?
Yeah, I've thought about doing that
That's
before.
something any
Yes.
machine can do.
That's right. I think it's a really good way to do this kind of thing. Right. I think exactly.
Now, syntax checking, whether it's correct, not well-formed formulas.
Mm-hmm.
I suppose you could do that, but that would be more expensive.
Yeah, I don't know enough about the computer side to figure out how to remove the human element. I think
well, in
that's a hard
geometry,
question.
You
But
came up with a really nice way where you've got
Well,
these
you
problems
don't wanna
like
put
case
yourself out of
and
a
geometry, building construction, right? So we say
we get
draw a
true
line
AI.
and draw a construction. Well, maybe for certain things,
That's not good as me.
let G be a finite group construction.
That's not
okay?
gonna happen.
Pick an element
Yeah.
of
You just need to
construction.
time it so you put yourself out of a job about the time you want.
exactly.
to
Yeah. Right. I want to cash in. You got it. Exactly.
I think many of the constructive proofs would be doable that way.
Hmm.
Because I'm saying George, uses Kasich and Geometry Explorer where you can say, okay, put down a line, now drop a perpendicular to that line. If you start stretching the first line, it'll still keep everything perpendicular to it. The thing is you drop perpendicular because it thinks of it in the higher sort of order of, it knows it's a perpendicular line to whatever line this is. Well, similarly, what if you say, let G be a group? Okay, drop that in. Now let X be an element in G. That's also a construction, and then you have a set of things that you can do to X
Mhm.
that the computer can verify.
I thought it was an
whether they're
exercise
correct or
of the axiom of choice.
yeah, but you build that in. You say, okay, I'm allowed to do that. So now it knows that X is an element of a group, and there's only so many things you can do with it. So I think for a limited set types of operations, one could do this sort of thing.
Yeah, and I think you're right. This stuff is on the
See,
dawn. I mean, this is going to
takes
happen
an
soon.
interesting viewpoint in Geometry Explorer. He says the Geometry Explorer is also a kind of axiomatic system. The buttons on the machine is an axiom. You don't question them. Constructions are not. They can become theorems. And he uses that analogy because this is the book on non-Euclidean geometry, where the one thing you're supposed to prove or get across is the concept of a model and the equi-consistency of non-Euclidean geometry.
Hmm.
Right? So he proposes, and this is a pretty hard concept to get across, but and certainly in his book he does that. He just makes the construction part axiomatic. It's an example of an axiom system that happens to be empirical as opposed to deductive. So
The hard part is to turn all that into actual practice, because we actually have flesh and blood students that have to get taught. That's a challenge, right? I mean, this is
no, yeah, you're right. It's hard to do. It's actually easier to do with people online because they don't get to discuss things orally. They have to figure it out.
They don't have to talk to you, is that what you're saying?
Well, listen, of course, what you missed out is a really resounding applause.
I'm really happy. Thanks very much. Thank you. Yeah, thanks for having me. This has been great. Yep.
What I like about you, Andrew, is that you always make me feel like I should raise the bar when I give talks.
Well, thanks. That's very nice.